With NC and NV known, the expressions of the number of carriers are simplified to what is given here. But it is still not easy enough to use, and we will do more simplifications to the Fermi-Dirac function. As kT is a relatively small number, which is just equal to 0.026 eV at room temperature, the exponential term in the denominator will dominate as long as E minus EF is much larger than kT. In such case, the 1 in the denominator can be ignored, and the Fermi-Dirac functions can be approximated by the Boltzmann's distribution. Graphically, that is shown in the figure here. The Fermi-Dirac function is given by the blue line, while the Boltzmann's approximation is given by the red line. The approximation is only valid for the conduction band for the case when EF is not too close to the conduction band. It is because value of Fermi-Dirac functions at EF is equal to 1/2, while the Boltzmann functions gives a value of 1. In later parts of the course, you will learn that the position of EF can be adjusted by doping, but we will not consider it at this moment. After the Boltzmann approximation, the relationship of the Fermi-Dirac functions of holes equal to 1 minus the Fermi-Dirac functions of electrons is no longer valid. A separate expression of the Boltzmann approximations for holes as shown here is required. After simplifying the density of states and the Fermi-Dirac distribution functions, we have all the tools to calculate the number of carriers in both the conduction band and the valence band. In the conduction band, we have the number of electrons equal to Nc times e to the power negative Ec minus Ef over kT. We denote this number as Ni to indicate it is the intrinsic electron concentration. And in the valence band, we have the number of holes equal to Nv times e to the power of Ev minus Ef over kT. We denote this number as Pi to indicate it is the intrinsic hole concentration. We know that the number of holes equal to the number of electrons in an intrinsic silicon, and we sometimes just label both of them by Ni, indicating the intrinsic carrier concentration. If we multiply them together, we obtain Ni squared equal to Nc times Nv times e to the power minus Eg over kT. The final expression shows that the number of carriers increases with increasing temperature and decreases with increasing band gap. This agrees with our understanding of the behavior of a semiconductor. To summarize the results, we usually quote the number of carriers of silicon at room temperature, which is 1.45 times 10 to the power 10 per cm cube. But engineers are lazy, and we generally just remember Nr equal to 10 to the power 10 per cm cube for simplicity. And this will be the number used in this course. Considering that the atomic density of silicon is around 5 times 10 to the power 22 per cm cube, or simply 10 to the power 22 per cm cube, the number of carriers released by the atom is extremely small. In the case of metal, each atom releases close to 1 electron. That's why intrinsic silicon is almost an insulator when compared with metal due to the small number of carriers.